I was asked to give a talk on, sort of a general talk on oceanic conditions in this region, and the title that I chose was this: Living Conditions in the Future Northeast Atlantic Under Climate Change. Now, first of all, let us all agree that climate change is here and it's here to stay. This is something we could discuss perhaps 10, 20 years ago. Now it is unfortunately a fact. The Earth, or at least the mean global temperature close to the surface, has increased by about 1 degree due to human activities. And it will continue to increase. How much depends on how much carbon dioxide and other greenhouse gases that we put into the atmosphere. If we look at this report, it came just a few weeks ago. It's from the Working Group 3 of the IPCC, Intergovernmental Panel on Climate Change, where they conclude that without a strengthening of policies beyond those that are implemented by the end of 2020, greenhouse gas emissions are projected to rise beyond 2025, leading to a mean global warming of 3.5 degrees by the end of the century, which is considerably more than committed or agreed in the Paris Agreement. But what does that mean, a warming of 3.2 degrees Celsius? This is actually, if you take the temperature close to the surface, average it around the globe, then the warming, that is what we mean by 3.2 degrees. But what will it mean for the Northeast Atlantic? Because different areas will warm differently. This figure is from another recent IPCC group. I think it came last August, Working Group 1. Simulated change, the different colors show you how much you expect the warming to have been by the end of this century relative to what it was pre-industrial. Note that this is assuming that the overall global mean surface temperature increases 2 degrees, not 3 degrees as it now looks to be. So this is an optimistic scenario. But you see, it includes very large differences, especially in the Northeast Atlantic. If we focus on that, you see there are regions where perhaps, according to this, and this is based on climate models, these huge computer programs based on physical and other natural laws and human activity. According to this, there are regions within the Northeast Atlantic where you perhaps will have very little warming, if any, whereas other regions will experience extremely much warming. So within the Northeast Atlantic, if we are to believe the climate models, in an optimistic scenario, there are very large variations. That's the first message. The second message is when you have such a large horizontal variation, it has to be a very, very good climate model in order to give you any accurate number, which implies that these numbers are highly uncertain. So that's a bit depressing. But and you may wonder, how can it be? If the climate modelers claim that they can calculate how much the Earth as a whole can warm under given conditions. It should be easier to calculate what will happen in a small region. But that's not the case. It's just the opposite. If you look at the globe as a whole, it's very much a question of how much energy comes in from the sun, how much energy does the Earth emit back into space as infrared radiation. And to a large, or roughly stated, the warming is equal to the difference between the two. And the reason that we have global warming is that we have increased the concentration of these greenhouse gases in the atmosphere, which partly block the energy out. And so you get a plus in this equation. It's fairly simple, and actually a Swedish scientist made some calculations more than 100 years ago, which still today are actually fairly accurate, as long as you talk about the Earth as a whole. But when you go and focus on a specific region, some other complications arise, because there are winds which bring warm or cold air into a region, and there are ocean currents which bring warm or cold water into a region. And if they change due to global climate change, then things may become quite different from what one perhaps expected. And that is especially relevant for the Northeastern Atlantic. And I'd like to document that with this figure showing the average sea surface temperature of the world ocean. Where it's red, it's warm in the tropics. Where it's blue, it's cold, close to the poles. But note that the black lines, they are isotherms, go through areas with the same temperature. They don't generally follow latitudes. And if you specifically focus on the 5-degree isotherm, here in the southern hemisphere, that's where it goes. In northern Pacific, that's where it goes. In both cases, water warmer than 5 degrees stays between 60 degrees north and 60 degrees south. But in the Atlantic, warm water extends much further north. Actually, nowhere else in the world ocean will you find as warm water as far away from the equator. And the main reason is that we have winds that bring warm air into the region, and we have ocean currents that bring warm water into the region. I'd like to illustrate that by a photo I took some almost 20 years ago. I got the opportunity to join a British research vessel going to Antarctic. And on our way, we passed a small island called Signy. And what was fascinating for me personally was that Signy is almost at the same latitude as the Faroes, only of the southern hemisphere. Although it's a bit closer to the equator, so you should have perhaps expected it to be a bit warmer. So we came to Signy in January, which in the southern hemisphere, as you know, is midsummer. And this is what Signy looks like in midsummer. Compare that to the paradise outside of this house, even though we are still a bit before midsummer. So yes, this region, the Northeastern Atlantic, is fairly special. And as I understand the system, the main reason for that is that we have this flow of warm water coming from subtropical regions, passing northwards. There's a weak branch west of Iceland, and then the two main branches go on either side of the Faroes, which are here. This warm water continues, sends one branch into the Barents Sea, one into the Arctic Ocean, and bringing along heat, which keeps large areas free of sea ice and large areas good habitat for immense stocks of pelagic fish. But of course, if you have such a continuous inflow into the region, you must have an outflow as well. Part of that is in the surface layers on both sides of Greenland, very cold water. But most of the incoming water actually sinks in this region because the atmosphere cools the ocean, so the surface water become much colder, therefore much denser, and so they sink and fill up all this part of the Arctic with very cold, dense water. Now this area, there is a submarine ridge extending from Greenland over Scotland and Faroes, from Greenland over Iceland and Faroes to Scotland, which partly blocks the exchange, but this cold, dense water pushes its way through the deep channels in the ridge in what we call overflow. There is a similar system in the Labrador Sea and to some extent also further east, but that's weaker. This system, the system as a whole is called AMOC, Atlantic Meridional Overturning Circulation. This is a word I believe most of you will have heard. I hope so. But I will focus on the northeastern part of the AMOC. And I would start, you may wonder why we are going through this. But the point is that all these flows are in some ways connected. And I'd like to convince you that this flow system in the Northeastern Atlantic, actually all of it, or most of it, is driven by cooling, atmospheric cooling. Just to demonstrate that perhaps in more detail, imagine that you take a vertical section going from the Arctic, crossing the ridge. And then, as I said, in the Arctic region, the cold air cools the surface waters so it becomes dense and sinks and fills up the basin, or bathtub if you want to call it, north of the ridge with very cold, dense water, and fills it up well above sea level so that you have a continuous outflow of cold, dense water spreading throughout the depths of the world ocean. On average, 6 million cubic meters leave or cross the ridge every second. That is 6 times as much as the water carried by all the rivers in the world. And that is forced by the cooling. But that cannot be all of it, because when you have such a continuous export of water here at depth, there must be an inflow as well. If there was not, the sea surface would start to fall. But as soon as the water, as soon as it has fallen say 10, 20 centimeter, there will be a slope in the surface across the ridge, and the water close to the surface will be pulled by gravity into the Arctic region. And that is the warm inflow. This is not the only mechanism, but this is, at least in my understanding, the most important mechanism driving not only the deep overflow, but also most of the heat import by the ocean into this region. And that is driven by cooling. And that is the problem. Because as you saw, with global climate change, the Arctic will warm much more than most other parts of the world. And then you expect perhaps that it will be less efficient as a cooling mechanism. In addition, we expect more fresh water from Siberian rivers and from melting Greenland ice sheet. And that decreases the salinity in the surface layers and therefore also density. So there has been a fear for a long time that global warming may make the AMOC as a whole, and also its northeastern component, weaken. As long as it's only a little weakening, well, of course, if you reduce this heat import to the area, then you expect less warming from that source. So if it's a weak, can one say a weak weakening, a little weakening, then this will just mean that the global warming will be less efficient here. If there's a strong warming, if there's a strong weakening, or if the weakening is large, then of course you might imagine that the loss of heat through this process actually could counteract global warming in this very specific region. And there are some processes involved here with positive feedback, which implies that if you push the system sufficiently much towards weakening, it may go into a vicious circle, inducing more and more weakening so that you even could get a collapse. We know that this occurred several times during the last ice age. Now conditions are, of course, very different, but this is a conceivable possibility. So, these are all speculations. What will happen in the future? The only way to answer a question like that is by going to the climate models. And again, this is from Working Group 1, IPCC. They, in their 6th assessment report, they state the Atlantic meridional overturning circulation is very likely to weaken over the 21st century. You may have noted that there are people who actually claim that this has already started. This paper got a lot of attention also in public media, but there are others who have claimed that. Now, we have been measuring this in our part of the world. When I say we, that is a large group of people from many different institutes around the Arctic. We've been measuring it for 2 to 3 decades. If you look at the deep overflows, the one through the Denmark Strait and the one through the Faroe Bank Channel, these are the 2 main branches. Together they account for 90% of the total. And this shows the development over Yeah, actually, we have updated versions of the graph. So over the last 25 years, certainly this did not weaken. And if you look at the warm inflow, the message is very much the same. No. Does that mean that the AMOC has not weakened? Well, not necessarily, because as I mentioned, there is a component also in the Labrador Sea. And some people claim that it has weakened, others disagree. I won't go into that. But this component, hey, so I switched it off, okay? Okay. So this component, our component, certainly did not weaken during the last 25 years. Of course, that does not necessarily mean that it will not weaken in the future. And as I said, if it does so, we expect global warming in this region to be less efficient. What we are perhaps more afraid of is the possibility of a collapse, which might induce cooling in some areas. And fortunately, IPCC concludes that there will not be an abrupt collapse before 2100. That's nice. Of course, when you see that there is medium confidence in this statement, that's not so nice. And even less nice is the fact that if you go to the previous assessment, almost 10 years ago, IPCC concluded it's very unlikely that the AMOC will undergo an abrupt transition or collapse in this century. So in the meantime, the climate modelers, or at least IPCC, have realized that while climate models are good at predicting many things, such as the global mean surface temperature given the forcing, they are not good at predicting the AMOC. We see that simply by comparing models with observations. The one thing that seems clear is that the more we perturb the climate, the more we affect it, greater is the probability that something dramatic, such as a collapse, could occur. So that brings me to my last slide. Living conditions in the Northeastern Atlantic will change strongly during this century. I'm fairly certain about that. I won't live that long, so I can make a statement like that, but I'm fairly sure that will be the case. But how those changes will be, they will be different in different areas of the Northeastern Atlantic. But how much each region, each area will warm or possibly cool is, as far I'm not able to say, and in my opinion, nobody is able at this stage. We are not simply, we don't have the tools to make these statements. I'm sorry about this. I suppose that in the title you expected me to give an answer to the title of my talk. And for those of you who will do mariculture in this region in the future, it's a bit depressing. But this is the world as I see it. But there's one thing more, and that is the more we perturb the climate, smaller changes are to be expected. So it just remains to thank funders over many years. Thank you.